We've seen some basic data types in Python, namely integers, booleans, strings, lists, tuples, and dictionaries. Now let's look at something which is very specifically useful for data processing, namely arrays. If we want to store a sequence of values in a programming language, there are two basic ways of doing it: arrays and lists. Arrays are what are used by languages like C, C++, and Java, whereas lists are what we have seen in Python. So what's the difference between these two? The main feature of an array is that it's a single block of memory. So it's a sequence of values which is stored one after the other in the memory, and typically the size of an array is fixed in advance. The main advantage of doing this is that we can get to any element very fast. Since everything is in a row, we know that we can find the ith element by starting at the first element and then marking off I blocks of the size of the element. However, in such a situation, it becomes expensive to insert an element between I and I plus 1 because we need all the values to be together. So we have to make space for it by shifting all the values from I plus 1 onwards by one space to make place for the new values. In the same way, if we want to remove an element and contract the list for an array representation where the whole sequence has to be together, contraction is expensive. In a list, on the other hand, the values are not in one place, they are scattered in memory. We achieve the sequence by having each element point to the list next. So in many programming languages, lists are referred to as linked lists because it is a value plus a link or a pointer to the next value. This allows lists to be flexible because we can always add a value after the current list anywhere where we have free space in the memory and make the current last value point to it. On the other hand, because the list structure is so flexible and the values are scattered around, we cannot directly find an element in the list by just knowing its position within the sequence. We have to start at the beginning and follow all the links and pointers until we reach the ith position. So this means that accessing A of I, the ith position in a sequence represented as a list, requires us to walk through I values, so it takes time proportional to I. On the other hand, because these things are flexibly linked together, we can always insert an element between two other elements by just shifting the pointers around locally. So we can do some kind of plumbing, just the way we can insert something in a piece of pipe by cutting the pipe and having a bypass. In the same way, we can bypass a pointer and add a new value. So how does this affect us when we use these sequences? One of the frequent things we need to do in a sequence is to exchange the values at I and j. This often happens, for instance, when you're trying to sort a list. We find that AI and AJ are in the wrong order, so we want to swap them. Now, if these are arrays, we know that we can find AI and AJ in constant time given I and j, and then it's easy to reassign the values back and forth. In a list, on the other hand, we have to walk to AI and then to AJ, so this takes time proportional to the values I and j. On the other hand, if we want to update the list by deleting or inserting a value, as we saw, in an array this is expensive because we need to make space or contract it, whereas in a list representation we can just do local operations and do it very fast if we are already at the position I. All these things affect the way that algorithms work. For instance, binary search is a clever way to find a value in a sorted list. We probe the middle element, and depending on the output, we either probe the first half or the second half. This assumes that we can find the middle element in a sequence fast. So it works very well for arrays, but not so well for lists, where it takes us time proportional to half the list to reach the middle element. So in Python we have lists. Are they lists or are they arrays? We have seen that Python lists are flexible, and this suggests that they behave more like lists than arrays. In practice, some optimizations are built in to make them a little bit more effective than normal lists. However, by and large, they are very much lists and not arrays. And also, as we have seen, they can keep values which are of different types, which is quite in contrast to what arrays do, because array elements must all be of the same type so that we can start from the beginning and mark off blocks of an equal size to reach the ith position. One way to incorporate arrays into Python is to use the package called Numpy. Numpy defines multi-dimensional arrays which are homogeneous of a single type. So essentially, you can think of a NumPy array as a table of numbers indexed by positions by non-negative numbers from 0 to n-1 in each direction. So let's run through some examples of how NumPy works. So first of all, you have to use NumPy, you have to load it. So the standard way is to load it and then give it a shorter name NP. So the first line just says import the NumPy library and use all the functions in NumPy with the prefix NP instead of NumPy. So one thing we can do, for instance, is create an array from a range of numbers. So the function arange in NumPy works very much like range. So arange 15 says give me the numbers 0 to 14. So if we say np.arange 15, we get an array whose elements are 0 to 14 and we can assign it to a name A. Having got these 15 elements, we might want to convert it into a different shape. For example, into a rectangular array with 3 rows and 5 columns. Reshape allows us to do this. So by saying b is equal to a.reshape 3, 5, we take a 15 element sequence, a single dimensional array, and convert it into a 2-dimensional array with 3 rows and 5 columns. In general, there is a function called array in NP which takes any sequence and converts it into an array. So remember that a list is a sequence and an array is a sequence, but we have to explicitly convert because lists are not arrays. So in this case, we give the list 2, 3, 4 and feed it to the function array, and we get an array with the same elements. But now this is a real array and we can index it and all very efficiently. The sequence need not be given as a list, it can also be given as a tuple. For instance, if we give a 2-dimensional sequence in which each element is itself a sequence, and here we have used tuples for the inner one and list for the outer one, we end up getting a 2-dimensional array with 2 rows and 3 columns. We can initialize an array by using zeros. So here, for instance, this function takes the dimensions 2 rows and 4 columns and produces a 0 valued array with 2 rows of zeros and 4 columns. Notice that the zeros have decimal points after them. That's because by default, NumPy assumes that an array has type float, in particular a floating point of 64. So we can find out the array type by using dtype. So by default, the dtype is float 64. Now here is another example. Arange we said behaves like range. So if we say arange 10, 30, 5, it's just like range. Start at 10 and go up to but not including 30 in steps of 5. So this is 10, 15, 20, 25 and then it stops because the next number would be 30. We can also create an array using equally spaced elements between a lower bound and an upper bound. Here, for instance, we want to create an array between 0 and 2, which is equally spaced, which has 6 values. So if we give it the lower bound 0 and the upper bound 2, and we say we want 6 values equally spaced, we automatically get an array of the following form, 0, 0.4, etc. So it splits the thing into 5 intervals, and these 5 intervals are of size 0.4. So there are 6 points and 5 intervals. One of the features of NumPy is that we can work with arrays as single objects and apply functions to all of them. For instance, if we want to apply sign or evaluate sign at 100 points equally spaced between 0 and 2 pi, then we can first set up this array using linspace with the lower limit 0 and the upper limit 2 pi and say that we want 100 equally spaced points. And then we can just apply sign to x. So what sign does is effectively it applies sign to each element of x. We don't have to write a loop. We can just feed an array to a function in NumPy and it will automatically evaluate at every element of that array. Here are some other operations that we can do on arrays. We can use them just like we do in algebra. We can create 2 arrays of size 4. In this case, we have created the first one explicitly using the array command and the second one using the arange command. And so now if we take A and subtract B, this means subtract B0 from A0, B1 from A1 and so on. So we get 20 minus 0 is 20, 30 minus 1 is 29, 40 minus 2 is 38, and 50 minus 3 is 47. We can do other things as well. If we say b square, that is b to the power 2, it takes every element in b and squares it. So 0 square, 1 square, 2 square, 3 square. Here is a complex thing. We first say take the sign of a. So it takes the sign of every value in a. So we get 4 signs, and then it says take it, multiply it by 10. So each element is multiplied by 10. So sign would give us a value between -1 and +1, and 10 will now 10 times that will promote it to a value between -10 and +10. We can also do this kind of array-wise comparison. So a less than 35 applies the comparison less than 35 to each element in a. Since 20 is less than 35, the first output is true. 30 is less than 35, the second output is true. And for the last two elements, because they are bigger than 35, we get false and false. We can also, not surprisingly, do matrix operations on arrays. So if we take two-dimensional arrays like this, and we do the normal star, which is the multiplication for normal arithmetic expressions, we get something that is slightly unexpected. We get the result of multiplying each element by the corresponding element in the other array. So here 1 times 2 is 2, 1 times 0 is 0, 0 times 3 is 0, and 1 times 4 is 4. If we really want the matrix product, which takes the row and multiplies it by the column for each entry, then we have to use at and not star. We can initialize an array to zeros as we saw. We can also initialize it to random numbers. So here is a way to initialize a 2 by 3 array of random numbers. Now we can apply some unary operations. For instance, if we want to add up all the elements in an array, there's a function called sum. If we want the smallest value in an array, there's a function called min. Similarly, there's a function called max to give us the largest value in an array. Just like lists, we can index and slice arrays. So here we start with an array of 0 to 7, and then we cube it, so we get a number which is 0 cubed, 1 cubed, up to 7 cubed. If we ask for the second position in this array, we get 0, 1, 2. So position 0 is 0, position 1 is 1, position 2 is 8. So A2 is 8. Similarly, a slice from 2 to 5 gives us 3 values at 2, 3, and 4. So 2 cubed, 3 cubed, and 4 cubed. Now, here is something which is slightly different. If we set a slice to a value, then it sets every position in that slice to a value. So if we say A3:6 is equal to -1000, then A3, A4, and A5 are all set to -1000. In an array with 2 dimensions, we can omit the double bracket. So if we want to refer to the second row, third column, in this case it is 0, 1, 2. So the row starting with 20 is row 2, and the column 3 is the last column. So we get the value 23. We can just write 2, 3 and not square bracket 2, square bracket 3. We can slice along one component or the other. So for instance, if we slice along rows and say we want all the rows from 0 to 5, and in that we want the first column, then we can write 0, 5, 1 and get this subarray. Here is another example. So here we take every column in the second row and the third row. So B1:3 says I want rows 1 and 2, and the second one says I want every column from 0 to the last column. We can operate on an array using a loop. So the basic thing is to think of an array as, again, a nested sequence of arrays. So if I say for something in an array, then it goes row by row. If I want to process the entire thing as a single flat sequence, row wise, then we can apply the command flat. So b.flat flattens it out into a single dimensional list and runs over each of them in turn. We can merge and split arrays. So the vstack command takes two arrays and puts them one on top of the other. So here you can see that we start with 8, 8 and 0, 0, the 2 by 2 array, and another 2 by 2 array, and we stack it, and then we get each array stacked on top of the other. Similarly, we can put them side by side and make a 2-row 4-column array. So either we can take these two things and make a 4-row 2-column array or a 2-row 4-column array, depending on whether we put the 2 by 2 matrices one on top of the other or one beside the other. And conversely, we can take an array and split it. So here, for instance, is a horizontal split where we take an array and say we want to split it into 3 parts. So what this does is it split it into 3 parts. So we have 12 columns in this. So the first 4 columns become one part, the second 4 columns become the second part, and so on. We can also say where we want to split it. So we can say that we want to split it after the third and the fourth column. So we can provide this kind of a argument to each split, in which case we get first a 2-row 3-column thing, then a 2-row 1-column thing, and a 2-row with the remaining elements.